Okay, guys, we're going to do a quick, simple pendulum example from some of the formulas we explained in the notes on the prior video. For this one's so easy, I'm not going to go to my notes to show it. I did it exactly the way it is done in the book, so I'm just going to go through it with everybody and explain it. It's pretty easy to follow. I'm on page 437 of your PDF textbook right now. But let me remind you of something very important. Just about simple pendulums with HM formulas. And I said a lot in the last video, but I'm going to say it again, that these formulas all came from the idea of approximating that the displacement angle where this thing is swinging from, theta, at small amplitudes, small thetas in radians, are approximately the same as the sine of theta. So it says in example 13.8, find the period and frequency of a simple pendulum. Let me stop right there. It says this is a simple pendulum right there. And if it says that, you could assume, even if we don't know what the swinging angle is, you may assume that we're at small angles right now. Because if we were not, basically, we couldn't find that without like an experimental version to find the period and the frequency, like using a stopwatch, right? But as long as we're assuming we're at small amplitudes, and we're going to assume that unless told otherwise, we could use some of the formulas in this section. So this will be pretty simple once we realize what we're allowed to use. A 1 meter long pendulum, that is length L, capital L, and the location we're at is G equals 9.8 meters per second squared. So the period is the first thing it asked me for. So the period formula, which we derived in our notes after realizing what the simple pendulum constant was and plugging it in for omega, that yielded a formula for time period, T equals 2 pi times the square root of L over D. So we literally just plug in those givens, run the numbers, and we get a little bit over 2 seconds. Now remember what that means, though. The time period of a pendulum, let's go back to this one, is the time it takes to go over and back, all right? Not just to one side. So let's wait till, I'm going to pause this thing, right? Okay. So if I timed how long it takes to go over and back, let me do that, over and back, right there. That's what this time represents in this example. And we should remember that the frequency, the regular frequency, not angular, the regular frequency F is the straight up mathematical inverse of time period T. So we inverse that and we get almost 0.5 hertz. Remember, in case you forgot, that hertz is how many cycles or vibrations per second. And here it makes the most sense to say cycles. So that means in 1 second, this pendulum goes through almost half a cycle. So let's go to this again. So remember, 1 full cycle is from there to there. So half a cycle is from there to there. From there to there. Okay. So frequency represents that it went through half a cycle in 1 second. How many cycles you get through in 1 second is what a hertz is. So hopefully that example was pretty easy to follow. There's really nothing much more to say about it. I think you guys are ready to do a practice on this stuff.